So in this lesson, we're going to look at some combination circuit theory. There's really no new theories here, but we're just going to apply the concepts we learned with parallel circuits and with series circuits. All right, so the first thing we want to do is take a quick look and just kind of refresh a few rules. So series circuit, there's only one path for current to flow. Kirchhoff's laws tell us because of that, we have current being the same everywhere in our circuit, okay? So the current doesn't change. Voltage, the voltage source of the battery is equal to the voltage drops across each resistor or each bulb. The equivalent resistance observed by the battery is equal to the sum of the resistances throughout the circuit. So just a really quick refresh of Kirchhoff's laws. Now we're going to look at a refresh of parallel. With parallel circuits, we discovered that the current changes throughout, and when you get to, we call this a junction point where it splits, the current goes in multiple directions. The current leaving the battery is equal to the sum of the current in all of the other branches. But the voltage or the push from the battery is equal to the push in each of the other branches. Now that's going to be a little different when we get to our combination circuits. You're going to have to think about where's the push being measured from. It won't always be directly from the battery. It may be push just from another section. All right, and then the equivalent resistance in a parallel circuit always decreases because there's more places for that current to go. So we use this really funky formula here, and yes, I have done nice easy numbers, so you can technically do all of it using simple fraction math. Okay, so just kind of refreshing those quick rules. So let's first think about just what happened to the circuit, and you've answered some of these questions in your simulation. So what happens to current as it flows through the circuit? Well, as current flows through our circuit, we have current that goes through resistor 1. It doesn't matter which direction we want to perceive current being from. We can do conventional current, or we can think of actual electron flow. But as current goes through a circuit, it's going to pass through resistor 1. It gets to this, what we call a junction point. I'm going to make a couple of marks here, just hopefully to give you, oops, let me see if my pen's behaving here. I don't appear to be communicating. There we go. We're good now. Yeah, we're good. I've got a little bit of lag going on here. Perhaps I need to plug in my computer soon. So when we get to this junction point, current splits. Okay, but at the other end, current recombines. Okay, so if we think about our path, all of the current that goes through this first resistor has to be equal to the current added up between these two, because the current leaves from this resistor, it splits, then it recombines and returns to the battery. So you'll see we're using some of our rules in parallel. We're thinking about where would current be the same? So the current is going to be the same through this whole section as it will be through resistor 1. Okay, hopefully that kind of makes sense to you. Throw it in the simulator, check, compare. All right, so what happens to the resistance in this circuit? Well, there's resistance from resistor 1, plus we have resistance over in this section. But we know this parallel section of the circuit has less resistance than if it was just a series circuit with resistor 1 and resistor 2, because at this point, current can flow through resistor 2 and through resistor 3, decreasing the overall current as compared to if it was just a series circuit. Now, that means we're going to have to think about what's happening in each component when we calculate our resistance. It's not overly complicated, but you just kind of have to think about what happens in each section. So we know this section, if I could draw this with one resistor, and if I could figure out what the resistance is of this parallel section, we could easily figure out the combined resistance of these two, because this parallel section, we call the parallel section, we say is in series to resistor 1. So everything goes through resistor 1, then it splits through resistor 2 and 3, and then recombines. All right? Well, what about voltage? Well, we know voltage drops at resistor 1, so we use some voltage here. So some of the push from the battery is reduced, but what about at this point? Well, the leftover push is going to be equal on resistor 2 as it will be on resistor 3. So we kind of imagine that this resistor, you can kind of almost pretend it's not there and think, what's the leftover voltage? That leftover voltage is going to get used by resistor 2 and 3. They're in series, so the voltage is going to be the same between the two. Now you'll see more of that as we do some calculating. All right, so this one, let's start doing. We'll do some calculations. I'm going to show you how I calculate, and we'll figure out, solve the circuit. So the question is, given the following values, solve the circuit for voltage, resistance, and current at each point. So what I like to do when I'm starting one of these circuits is I'll label E, I, and R at each spot. I don't like using a table for this because it gets a little more confusing. Okay, so we have our E, I, and R for each spot, and let's label those with each of their values. So what is the value for each? So the battery has a voltage of 12 volts, so that's E. Or you could use V if you want. Resistor 1 is 4 ohms. Resistor 2 is 2 ohms. Resistor 3 is 4 ohms. All right, so in order to solve this circuit, we know we need to figure out at least current at some point. The only way we can do that is we need to know what is the resistance the entire way through the circuit. Well, how would we do that? Well, as I said before, this section of the circuit, if we could combine it, it's parallel. If we could combine that section, we would end up with, I'm going to do a redraw. We're going to have a battery. I'm not going to maybe draw as many lines. We're going to have our resistor 1. And this would be, if we combined, I'm going to call it R23. If we combine resistors 2 and 3 together, it would look like that. Would you know how to find the resistance in that circuit? I think you would agree that that's a series circuit, and it would be easy to calculate the resistance. So let's figure out, what is the resistance of 2, 3? Well, this is parallel. So to find out the resistance of 2, 3, we'll find the equivalent resistance. We need to use our parallel circuit math. So 1 over R23 is equal to 1 over R2 plus 1 over R3, which is equal to 1 over 2 plus 1 over 4. I'm going to let you come up with the equivalent fraction. So we'll have 1 over 2 becomes 2 over 4 plus 2 over 4. And we get 1 over R23 equals, whoops, did anybody catch my mistake? I meant to write a 1 over 4 and I wrote a 2 over 4 here. There we are. 1 over 4, so that gives 3 over 4. So we have R23 is equal to 3 over 4 flipped would give me 4 over 3, which is 1.33 ohms. So we can actually go back and we can do some solving in this circuit. So we could say, okay, these two are equivalent. So if we say that this is 1.33 ohms, and we know this one is 4 ohms, the resistance at the battery would be 5.33. That's exactly what we have over here. All right. So you see, it's kind of a little bit of all over problem solving. So the first thing I do is I see, are there any sections I can combine to make it look more simple? So we combine the parallel section to make a simple series circuit. That gets rid of some resistors for us, and then we combine the two series. Then I fill in and I go, can I use Ohm's law anywhere? Well, we can use Ohm's law at the battery. Ohm's law says that current is going to be equal to voltage divided by resistance. And voltage divided by resistance at this junction point gives us a current of 2.3. Now let's follow from the battery. We're going to work our way through. We're going to use current and see is there anywhere where that's going to be the same. Well, if we leave the battery, we have a resistor in series to the battery. So it has to share the same current as the battery, which is 2.3 amps. Now notice we have current and resistance. Voltage is equal to current times resistance. So 2.3 times 4, and 2.3 times 4 is going to give us 9.2 volts. So we just figured out another piece. I'll underline the ones we've calculated just so that you've got those. Okay, now if we continue with that current, well, we get to this point and the current splits. You don't know how much current goes in each branch. So we're kind of stopped. We have to wait. Could we figure out the voltage on each branch? Well, we know the voltage, so I'm going to put voltage in here. So we're going to say E is equal to 9.2. So at this point, if we were going through this circuit, if we just had this circuit, and we knew that we had 9.2 volts at this resistor and 12 volts at the battery, in a series circuit, the voltages add up. So we would know that the voltage at 2,3 has to be equal to 2,3 plus 9.2 equals 12. So in order to solve for it, I'm going to say, well, this is equal to 12 minus 9.2. And 12 minus 9.2 leaves us with 2.8. So I'm going to fill that in. Now these two sections, so I've got 2.8 volts to use up in this section. Because they're parallel, the voltage is the same in each branch. So I do 2.8 and 2.8. Now we can figure out our current. Okay, so 2.8 divided by 2 gives us 1.4 amps. And then over here, we have 2.8 volts divided by 4, which gives us 0.7 amps. Now, if we look, the current in these two branches should be equal to the current through resistor 1. 1.4 plus 0.7 gives us 2.1. Because we had to round that 5.33, it's made a little bit of difference in our current, but we've still calculated it correctly. Now I'm just going to do a quick pause here. I'm going to plug my computer in and right, so now let's look at another circuit. So if you had questions about the last one, that's okay. We're going to do a couple more. And as we go through a couple more, I think you'll understand some of it better. So this circuit, we have a parallel circuit with a series section in one of the branches. Okay, so the first thing I'm going to do is the same thing I did before. I'm going to label all the pieces, and then I'm going to go through kind of my logic process and see, is there anything I can combine to make it down to 2 resistors instead of 3? So we have E here is 12 volts. I don't know current, and I don't know resistance. Resistor 1, E I don't know. Oh, do I not know E? Resistor 1 is parallel to the battery. Because it's parallel to the battery, it's going to share the voltage from the battery. I don't know the current, but I do know the resistance. It tells me it's 3 ohms. Resistor 2 and resistor 3, we don't know the voltage for each of them, but I do know resistance. 2 ohms and VIR is 4 ohms. Okay, now the first thing I would do is let's pause and see is there anything we can calculate. So if you look over here, we can use Ohm's law because we have 2 out of the 3 pieces. So current is going to be equal to 12 divided by 3, which is 4 amps. So we just calculated another piece of information. Well, what else can we use anywhere else? Is there anything else that we can, well, we don't know current from the battery, so we can't just subtract to find the current over here. So we need to figure out what is the total resistance in the circuit. So let's look here and see. Do you know how to combine resistor 2 and 3? Well, R2, 3, they're in parallel. I just said parallel. They're in series. Because they're in series, their resistance is add. So it's going to be equal to R2 plus R3, which is equal to 2 ohms plus 4 ohms, which gives me 6 ohms altogether. And I'm going to do the same thing as I did before. I'm going to redraw it. So I have a battery. I'm getting sloppy in my drawing here. I got a resistor, and then I have another resistor. Okay? When I drew my other circuits, I do them out on grid paper first, and then I scan them to PDF, and then I cut and paste and drop them in to make them look a little prettier. So they're a little bit time consuming to do, but it makes the diagrams look a little better and a little straighter. So this is our redrawn circuit. We still would have 12 volts here. At this point, we know that we have 3 ohms, so we calculated that, and this would be R2, 3, which is equal to 6 ohms. Now you'll see these are just a parallel section. They're easy to add up. We know that already. It uses the ugly formula. So 1 over REQ is going to be 1 over 3 plus 1 over 6. Make a common denominator. 2 over 6 plus 1 over 6, which gives me 3 over 6. So my equivalent resistance is going to be 6 over 3, which is equal to 2 ohms. So I can put that in here. Can you use Ohm's law yet? We can. We can use Ohm's law here. So current is going to be equal to 12 over 2, which gives me 6 amps. So 6 amps leaves the battery. If 4 amps goes down this section, we know 4 amps has to go through this section as well. So, oops, so not 4 amps, the remaining 2. So we get 4 amps goes this way and 2 amps goes that way. It adds up to be a total of 6. So we're going to have 2 amps and 2 amps. Voltage is current times resistance. So we have 8 volts, and this one's going to be equal to 4 volts. Now the voltage, this is 444, 4 volts. The voltages should add up. So 4 plus 8 is 12. That matches this section because the push coming into this branch with 2 resistors is equal to 12 volts because it sinks to, it goes back directly to the battery. Does that make a little bit of sense? Is there one of them that maybe is easier to figure than the other? There's probably one that makes more sense to you than the other one, and that's okay. That's perfectly logical. Now we're going to do just kind of a couple discussion questions with it, and then I'm going to solve one more for you. So for this one, I want you to think about what would happen. So we can use a switch to simulate a break. Okay, and I think about breaks in electrical circuits because we recently had a vehicle with a break in one of the wires in the door, and it was impacting how whether we could roll our window up or down. Sometimes it would work, sometimes it wouldn't. Sometimes you thought you heard the motor starting, sometimes you didn't. So what would happen if we have a combination circuit and there's a break? Is everything going to stop? Is only some of it going to stop? What's going to occur? Well, so let's say this is connected. Let's say we close the circuit. If it's closed, current is going to flow from the battery. It's going to go through branch 1, and it's also going to go through branch 2, 3. Now, because this is parallel, it's going to have a decreased resistance, and but it's also going to see more current. A lot of current come from the battery because there's 2 possible branches to go through. Let's compare it to, well, if the circuit is broken, if there's a break here, I'm going to erase that. If there's a break in that section, we are going to find that the current can only go through this first loop. So let's compare the first loop to the second loop, or to both loops. Okay, so there's our circuit. Okay, so what's going to happen between the two? Well, this circuit, I'll close the switch, this circuit is going to have more resistance. Why will it have more resistance? Because there's only one path to go through. And when you have a parallel section like this, the sum of the resistances is always smaller than what you started with because there's more paths for it to split through, so more current can flow from the battery. So this one's going to see more resistance, but if it has more resistance, it's going to see less current. Whereas this one will have less resistance, but it'll have more current. So we could use you could use a voltmeter to kind of predict what's happening, even if you don't exactly know where the break is. If you're in part of that circuit, if you know what the voltage should be, or what the current should be, or what the resistance should be, you could figure out, is the circuit broken, and in which section is it broken? If there was a break here, we would see a lot more resistance because, well, I shouldn't say a lot more resistance than parallel, we'll put it that way, because resistor 2 and 3 are going to be slowing down a lot of the current. Okay, so that would be if we put our switch here. So we can kind of look, there's multiple things that happen in these scenarios. I kind of think, what happens if this breaks? How does the current go up? What goes down? If resistance goes down when current goes up, we call that inversely proportional. You did that last semester. I'm going to give you a doozy to figure out. It's really not as bad as you think it is. We want to figure out what the voltage, resistance, and current is in this circuit. So this is just a calculation. The first thing I do is I kind of go through and I figure out what's my section. So I know this section, R2, resistor 2 and 3, is a parallel section. I know that I could solve for the resistance of those two and redraw it to look more simple. So that's where we're going to start. But first, I like to, you know me, I put my voltages in. So we have E, I, and R at each spot. E, I, and oops. Not sure what's going on here. Flipping back and forth for some reason when it shouldn't be. All right. EIR. And we have 3 ohm. Oops, that's the 6 ohms. Resistor 3 is 6 ohms. Resistor 2 is 6 ohms. Resistor 1 is 5 ohms, and resistor 4 is 2 ohms. All right, so let's go through and we're going to figure out what we can solve. So let's do this parallel section first. Let's see if we can add those together. So we're going to combine R2, 3. So resistor 2, 3 is parallel, so we have to write it the parallel way. So it's going to be 1 over R2 plus 1 over R3. We do the flip. R2, 3 is equal to 6 over 2, which is equal to 3 ohms. Okay, let's redraw our circuit and see if we can solve another piece. Okay, so in order to redraw this circuit, how are we going to do that? So we have a battery. And then we have a parallel section. We have parallel to the battery. And actually, since you know this one, that branch 1 is parallel to the battery, you could actually fill in the voltage as 12 volts here right now if you want to. And that's going to tell you your current at 1 at that point, which 12 divided by 5 gives us 2.4. That gives us just one of the little pieces that we can calculate. We still have to work through the rest of it. That gives us one of our sections. Now here, so we've got this resistor. We know this is 5 ohms. And then we have R2, 3. So we just combine them together. And they are connected to R4. So if we look, if we take these two, if that was all we had in a circuit, they're series. Okay, so we can say, well, R2 plus 3 plus 4 is equal to, if they're series, that's going to be equal to 3 plus 2, which is 5 ohms. Okay, I'm going to redraw again. And we got our battery still. We still have that parallel section at the beginning, and these two are parallel to this resistor. So now we have a circuit that looks like this. This is 5 ohms, and this is 5 ohms. So how do we add them together? We're going to have 1 over REQ. And we're right down to the battery. So is 1 over 5 plus 1 over 5 REQ equals 2 over 5. Whoops, 1 over REQ, or the total resistance is 5 over 2, which is equal to 2.5. So we can go back and we can look at the end. We got 2.5 amps or ohms, 2.5 ohms there. So 12 divided by, 12 divided by 2.5 gives me 4.8 amps through that section of the circuit. So 2.4 amps are used here. So that must mean this whole section, so there's, if 2.4 amps comes down through this branch, that must mean that there is 2.4 amps going through that way, which means it has to recombine and give me 2.4 amps here because we redrew this. There's 2.4 amps. We said, well, these parts are series. So 2.4 amps here and 2.4 amps here. So we can figure that out. And that gives me voltage equal to 2.4 times 2 would be 4.8 volts. Okay. So we started out with 12 volts. 4.8 volts gets used here. So how much voltage is left for this section? Or you can think of it this way. We just figured out that the current in this section was 2.4 amps. So what's the voltage you would get in that whole section? And we get 7.2. And because 2 and 3 are parallel, they're going to have the same voltage. And that lets us figure out our current. Our current should add up to the current at 4. So we're going to do 7.2 divided by 6, and you get 1.3. 1.3. Which gives us 2.6, and it's just because of rounding that it's giving us 2.6 instead of our 2.4. Anytime you get those 0.333 or 0.666 repeating, it'll often give us a decimal that doesn't quite add up, but it's really, really close. Right? That one is probably a little bit confusing, but again, the process is break it down simple and calculate. Now, 2 other questions to think about. This one I really like. I'm going to hide this video. You don't need to see my face right now. If resistor 2 shorted out and acted like a wire, what would happen to the current in the circuit? Well, we're thinking about how does it, because a combination circuit is quite common to have. It allows us to power multiple things. So resistor 2, if it shorts out and acts like a wire, we're going to just draw a wire here instead. Now let's trace our current. So we have a current path that can split here. Current always takes the path of least resistance. So would it go through just a wire or would it go through the resistor? Well, it would go through just the wire. So current is going to take this path with no resistance here. It's going to skip this one because it's going to take the path of least resistance. In real life, you get a teeny little bit of current there, but for the most part, not. Just because wires have a little bit of resistance. All right, so what happens to the current? Well, if it's only going through one resistor, instead of the equivalent of having 2 resistors, because we could redraw this as a second resistor, it means we're going to have more current. Why is it going to have more current? Because we could redraw our circuit with just one parallel resistor. It doesn't have to go through this section too. Okay, so it's going to have more current, but it's going to have less resistance. We could figure out, if you knew what the values were, you could figure out what would the values be at each of the particular spots. But it's thinking about how is the current going to flow, what's going to happen. Well, what about another scenario? What if resistor 2 burns out? It acts like a brake, so it's got a cut. Well, what happens to current if it cuts? Current gets to this point. Can it flow through resistor 2? Well, no, there's a break there. So we omit this branch. So it's broken, there's no flow. So the current is only going to flow through resistor 1 and resistor 3. Well, because normally extra current could flow through here, that would make this section have less resistance. Now when it goes all through resistor 3, it actually causes the resistance to increase. So the resistance increases and we're going to find there's less current. So we're just kind of using logic to figure out what would happen, and you could go through and you could calculate. These are really simple circuits. You could build them in the simulator and see, double check them and prove that that's actually what you see. Now, I always like to ask questions about what happens if a resistor burns out, because you can use math to prove what happens, or you can just use some simple logic to prove what would happen and how it would impact the values that you would expect to read, or if you suddenly get a funny reading, what it might be. All right. So that finishes off this section, and next I'm going to talk just a tiny little bit about transformers, and then that has our electrical completely finished and you're ready to do your assessment.